Hello again. I'm Michael Ekstrand, the lead developer and founder of the LensKit project. And in this video, I'm going to walk through an example LensKit recommender to show you the pieces of how a recommender algorithm built in LensKit works. LensKit can seem big, complicated, and daunting sometimes. So this video is going to walk through a minimal but real and complete implementation of a recommender algorithm for LensKit to show you what the pieces are and how they fit together. The example code I'll be talking about is the recommender algorithm that comes with the fancy archetype. So if you create a project using the fancy archetype from LensKit, you'll get the code that I'm about to show you. An archetype is basically Maven's concept of a project template. So they're deployed to the Maven central repository, available through there. You can use Maven to create projects based on these archetypes. So the main components of a LensKit algorithm implementation are typically three classes and then the other ones that they require. The item score is the heart of most algorithms. The item score interface in LensKit is an interface that provides user-personalized scores for items. Most of the time, if you're creating a new algorithm in LensKit, you're creating a new item scorer. Our default top-end recommender will generate recommendations using that score. Our default rating predictor will use those scores and clamp them to the rating range to output rating predictions. But the item score is where the heart of the logic for a lot of common recommender algorithms lies, computing these user-personalized scores for items that can be used to rank recommendations or to generate rating predictions. So most of the time in LensKit, if you want to say, I'm going to use this algorithm, really what you tell LensKit is, use this item scorer. Item scorers often use some form of a model of pre-computed data to aid their computations. This model can be an item similarity matrix. It can be just a table of pre-computed mean ratings for each item. That's what the model and the code we'll look at in this video is. And these models are separated from the scorers so that they can be built and then they can be serialized to disk, reloaded, etc. So you can have one machine that processes your data, builds a model. You write the model to disk. You then load the model up in your web server in order to serve recommendations to your users. Then we typically have a separate class that does the model build. So the model build code is separated from the model itself. It keeps the code nice and cleanly architected. So let's look at how this code works out in practice. So I'm going to start by using the Maven archetype to create a new project. And you can do this from your IDE, from Eclipse or from IntelliJ, but I'm going to do it from the command line, and then I will import the project into IntelliJ. So to generate a new project with an archetype using the command line, the command is mvn, which is the main Maven command, archetype:generate. And this will scan the Maven repositories and my local repository for available archetypes, and then it will prompt me for them. And it gives me a list of 839, which I don't really feel like scrolling through, so it lets me just search. So I can type LensKit. And this will filter the list to show me the LensKit archetypes. I want the fancy one, which is number 1, and then I want version 2.0.1. Now it'll ask me for a few properties for my new project. The group ID, which is how Maven part of how Maven names projects. I'll just do org.group.lenskit.demos. And I'll call the project LensKit example. And the version's fine. I don't really care about the version for this demonstration. And go ahead and reuse the group ID for the package name. These are the settings I gave it. I like them. I'll tell it to create the project. Now, it's created a project in the LensKit example directory. And this is a Maven project, which most modern Java IDEs can import and interpret just fine. So now I'll start IntelliJ. and I will import, or I will open. IntelliJ, you don't actually have to do an official import. You can just open the Maven project, and IntelliJ will handle that just fine. So I'll go browse to where I created the archetype, and I will open the pom.xml file as a project. IntelliJ will scan it. And now I have my project. To show that everything works, I'll run the project. So to run it, I'll go to Run and tell it I want to run. And I don't have any run configurations yet, so I'll edit configurations and add a new one. And I'm going to add a Maven configuration. And I'm just going to run the entire LensKit evaluation toolchain on it, which we'll discuss in more detail in another video. So I'll run the LensKit publish Maven goal. And while it's running, we'll look at just a few things. First, the pom.xml is the Maven project file that defines the project source code, its dependencies, and things. So there's a variety of properties in here. We set the LensKit version that it's using as a property just to make it easy to update the version. It says that this program depends on LensKit, the core, the KNN recommenders. We also use JUnit for testing. And then it has a few options such as using Java 1.6 compatible code and then setting up the LensKit evaluator. So the project source code is like all Maven projects under the source directory. And the code implementing the algorithm is in source main Java and falls into three pieces. First, we have the extended item user mean scorer. And this is an implementation of item scorer. And it implements a simple user item personalized mean. So it takes the average rating for each item, and then it computes how much on average the user likes items with respect to the item averages. So does the user tend to like items more or less than the average user? And it combines these two means. So you get a score that's just basically a linear regression to predict a rating across using user and item as the predictors. So this class, it extends the abstract item scorer, which is a helper class that implements several of the methods of the item scorer interface in terms of one, to reduce the work that you need to do in order to implement your own item scorer. We have a few fields in the item scorer. We have a user event DAO, and the DAO stands for data access object, and it's how LensKit provides access to the data underlying your recommender. The user event DAO lets you look up events or ratings in the system by user IDs. You can, given a user ID, say the user that you want to score for, you can look up all their ratings. We also have a user damping term to implement a slightly damped mean to keep from assuming that the user's 1 5-star rating means that they like everything a lot. And then we have the model. And in this algorithm, the model is just a pre-computed table of the mean and rating for each item. We then have a constructor that takes these three parameters and just saves them away into the fields. This constructor is annotated with the @inject annotation. And that tells LensKit and the dependency injector that LensKit uses that this constructor is supposed to be used to automatically build the item scorer. If you're familiar with tools such as Juice or Pico Container or Spring, then you've seen dependency injection at work where the toolkit automatically instantiates your objects using constructors like this. LensKit uses an injector called Graft, which is in many ways very similar to Juice. So it will take this constructor, it will look at its parameters to get the dependencies. In this case, we depend on the DAO, the model, and then this damping parameter, and it will automatically instantiate them and supply them to the scorer. Then I'll skip over this helper method for just a minute. The score method is the heart of the item scorer. And it takes a user ID, and this is the user that we're personalizing the scores for. And it takes a mutable sparse vector. And this vector is both an input and output parameter. So the vector will contain in its key domain, which is the set of valid IDs, or of IDs that vector can contain scores for, all the items that the caller wants scores for. And the job of the score method is to populate that vector with scores. And it's supposed to just overwrite whatever's in the vector already. So to do that, the first thing we do is we get the user's ratings. We ask the DAO to get all events of type rating for the specified user. If it's null, that means that the system doesn't know doesn't know anything about this user. So we just use an empty set of ratings for that user, which will give them a mean offset of 0, as we'll see in just a little bit. We then convert their ratings into a rating vector. And the rating vector is a vector that maps item IDs to the user's ratings. And this rating vector user history summarizer is responsible for doing that, and it just has a static method to make a rating vector from a profile. This deals with the case where your data source remembers multiple ratings. So if the user re-rates an item and you keep track of all of those ratings with timestamps, the make rating vector will automatically just use the most recent rating as the user's rating, and it gives you one rating for each item the user has rated. We then call this helper method compute user offset, which computes the user's average offset from item mean. And we'll talk about that in just a minute. With that offset, though, it then does the score, fills in the scores. And it uses bulk methods on the sparse vector to do this efficiently. First, it fills the entire vector with the global mean rating. And even if the user has no offset and we've never seen that item before, global mean is exactly what we want to score that item with. We then add the offset, the item offset, for every item. And the item offset is the difference between the item's average rating and the global average rating. We then add in the user's mean offset to finish the scoring computation. Let's take a minute now and go to a piece of paper to look exactly what this formula is. So the scoring function that we're doing here is this user personalized mean that is the score for an item, or for a user U item I, is equal to the global mean rating plus the item score plus the user score, or baseline, or the user score. And I'm just calling these B's because we often use these things as baseline recommenders. So the mu is just the global mean. B sub I is the item offset. And B sub U is the user offset. And B sub I is equal to the sum over the users that have rated the item of that user's rating minus the global mean all over the number of users that have rated the item. The user baseline, the user score is basically the same thing for users. Over each item the user has rated, the user's rating, minus that item's baseline and then in both of these we just put in a little damping term gamma to decrease the extremism of means based on very few ratings. So that formula is exactly what this sequence of vector operations implements. We fill everything with the global mean, we add in each item's offset, and this version of the add method takes a vector, takes all the items that are in both vectors, and just adds the value of one to the other. And then we add in the mean offset. And with mutable sparse vectors, the vector itself is being modified. The vector that you're invoking the method on is being modified. And this pattern, which might be slightly familiar to those of you who have done Fortran programming using a tool like BLAS, allows us to very efficiently do many computations and just accumulate results into a vector. So the user offset computation, this helper method we skipped, if the ratings is empty, we just shortcut and say no offset. If the user doesn't have any ratings, we'll just use item averages as their scores. Then what we do is we create a mutable copy of the user's rating vector. So this method can freely modify this copy without having that trickle out into the caller. We then subtract the global means. We subtract the item offsets. And this means we now have a vector of user offsets from item means. And we then just compute the damped mean. We take the sum of the vector, we divide it by its size plus this user damping term. And the user damping term is usually going to be small, something like 5, so that once the user has quite a few ratings, the damping term is effectively irrelevant in the final computation. So now that we've seen this, let's look at the model just a little bit. And the model for this is very simple. It consists of a global mean and a vector of item offsets from that global mean. So that global mean plus item offset is the item's average rating. Now, this class does not have an @inject constructor because we use what we call what's called a provider to build it. So this default provider annotation tells the dependency injector to use when it needs an item mean model, don't look for an @inject constructor. Instead, instantiate an item mean model builder, which might have its own @inject constructor and its own dependencies, and call its get method to get one of these. And it's not necessary. We could implement all the logic in the item mean model constructor, but I prefer to keep my constructors simple and basically have them just copy data around and do some light computations. If there's heavy lifting to be done, I prefer to have that in a builder class to keep the code clean and the classes simple. There's also this shareable annotation. And typically, models have this annotation. And what it means is that this annotation is serializable, and it's thread safe, and it doesn't depend on any DAOs. And that means that LensKit can build it, it can write it to disk, it can load it back up in a web application or a different environment, and it lets you move your models around between environments. So the model, this class is very simple. It just has the global mean, the item offsets, and getters so that the scorer can get both of them. The interesting logic is in the model builder, the item mean model builder. And it implements the provider interface of item mean model, and it has a couple of parameters, damping, and it has a DAO, an event DAO, so we can get all the ratings, and compute the average rating for each item, and the global mean rating. So it has an @inject constructor that depends on both the event DAO and this mean damping parameter. The event DAO is annotated with this annotation @transient. And @transient goes with @shareable. And @transient really only shows up on constructor parameters for model builders. And it tells LensKit that the model builder will use the DAO to build the model. But once the model is built, it does not contain a reference to the DAO. So the DAO is no longer needed once the model is built. And this enables some of LensKit's advanced features for automatically working with recommender configurations. And there's not this condition that the model cannot use the DAO once it's built is not enforced. It's a promise that the model builder makes to LensKit. And if that promise is not upheld, things can break. And if you'll remember from the model, it doesn't have any reference to DAOs of any kind. So the logic for the model builder is typically in the get method. And get is the only method defined by the provider interface, and it's just called to get whatever that provider is supposed to provide. A model builder provides by building the model, typically. So in this, we're going to compute some averages. We're going to compute the average rating for each item, and we're going to compute the global average. So we initialize a total and a count for the global average. We create a map that we're going to use to accumulate the sum of each item's ratings to compute its average. We then initialize that to have a default return value of 0. And this is a fast util map, which enables very fast operations on maps that don't have boxing overhead when you're working with primitives like longs and doubles. It also has a feature that lets you specify what's going to be returned if the key you look for isn't there. So this just means if a key is not there, it's 0, which is exactly what we want. If we haven't seen an item before, then it has no rating, so its total rating is 0. We do the same thing for a map of counts. We then get a cursor. Now a cursor is basically an iterator. It also implements iterable that just returns itself, so you can use a for each loop with it. That is also that needs to be closed when you're done, so it could be backed by a file. It could be backed by a database connection. And it gives us a way to stream things into LensKit classes in a type-safe fashion. So it asks the DAO to stream all events of type rating. And we have a try finally, so we close the rating cursor when we're done with it. We then loop over each rating. Now a rating contains a preference, and the preference is a user item rating triple. And if the preference is there, that means the user rated. If the preference is null, that means the user unrated the event. Most data sets you don't have unratings, but the LensKit data model handles unrates as a general case. So we get the item ID, the value from the preference. We add the value to the total, global total. We increase the global count. And then we just increase the sum and the count for this particular item, taking advantage of the fact that they'll return 0 if we've never seen the item before. After we've counted up and summed up everything, we can compute the global mean. And in all of these, to keep things well defined, we just use 0 if there's no values, or no ratings whatsoever. The global mean's easy. We then create a vector that's going to hold the item means. So we create a vector from the item rating counts key set. So that's all the items we've seen. We're going to create a vector that can hold those keys. We then iterate over every entry in the vector. We use fast iteration. Fast iteration is a pattern that LensKit borrowed from the fast util library. And what it says is that, what it means is that this vector entry is only going to be used within this loop, and it's not going to be kept or referenced by any other code. So for each time through the loop, we could modify and reuse the same vector entry object. Since vector entry is a flyweight, we don't want to create too many of them if we don't have to. So fast is just a shorthand to tell the vector, lets the loop tell the vector that the entries are not going to be referenced outside of a particular loop iteration. So feel free to mutate and return the same vector entry rather than creating a new one each time through. It makes the code it puts less pressure on the garbage collector. So then we get the item ID for that key. We also say that we want the state either. We want both set and unset. So this vector, it's going to have all the keys as valid keys, but none of them are set. So if we just iterated the vector, it's an empty vector. We're not going to get anything. But we say vectorEntry.state.either to say give us all the entries irrespective of whether or not they are set. We get the key. We then get the item rating counts, throw in the damping term. We get the sums. We also throw in the damping, and we put the damping in the numerator as well. Algebra shows this to be equivalent to the formula I showed you on the paper. And if the item count is positive, then we set the damped mean minus the global mean, so it's an offset, into the vector. We then return an item mean model that contains the mean and an immutable copy of the vector using the freeze method. So that's a walkthrough of the main components of a LensKit, a working functional LensKit recommender algorithm. I hope you find it useful for getting your bearings as you work with LensKit and read the documentation.